Hello, welcome back to the Metabolic Classroom. I'm Professor Ben Bikman, a biomedical scientist and professor of cell biology. Thanks for joining me for the lecture today. The topic today is hyperglycemia. That is the technical term for high glucose in the blood. What I want you to appreciate is that much of the time we're going to spend together is going to be focusing on the consequences of hyperglycemia in acute moments. So this doesn't, by that I mean, it's easy to think of hyperglycemia as a problem when glucose levels are chronically elevated. I'm going to start with that, but then everything else we talk about is consequential even in acute glucose spikes. That's indeed part of the motivation for this topic was me seeing people saying there's no problem with spiking your glucose. I actually appreciate that sentiment, that I don't want to be a fearmonger and making people think that if you're looking at your CGM and you see your glucose levels go up and down, I don't want you to think, oh, great, now I'm dying. No, I don't mean to be that dramatic. But I do mean to convey the ideas based in literature that, in fact, there are consequences to that are pathogenic, that are relevant to disease states. All right, now let's start with the consequences of hyperglycemia when the glucose levels are chronically elevated. This would be, something like diabetes. Now, the word diabetes is interesting because it actually is a term that describes the most famous symptom or manifestation of chronically elevated blood glucose, which is a lot of urine production, something called polyuria. Diabetes essentially means too much urine is being produced. It is the Greek word for the word siphon or flowing through. And it is, of course, a direct term relevant to the fact that if glucose levels are too high, you are overwhelming the kidney's ability to reabsorb that glucose. So just by way of a brief primer on kidney physiology, the operating unit or the kind of business unit of the kidney is this glomerulus, this little set of capillaries wrapped up. So the blood side and then the kind of kidney side. And it is this little set of capillaries where the blood is flowing through, and then it is encapsulated in this thing called a Bowman's capsule. And you have stuff that is moving from the blood, the capillaries, into this capsule, into the Bowman's capsule. It's capturing it and then moving it into the kidney tubules. Now, as I'm acting this out, if you're watching, in this arm here, which is the kidney side absorbing stuff from the blood, what is now going down the length of my arm, but down the renal tubule in the metaphor, that's going to be ultimately excreted into the urine unless it gets reabsorbed. And so when glucose gets filtered at the glomerulus, it will get reabsorbed. And so the actual amount of glucose that comes into the urine is very, very modest, essentially none. In a healthy person, there will be no glucose in the urine. However, if there's so much glucose in the blood, that means there's so much glucose getting filtered into the renal tubule through the capsule that we've overwhelmed the kidney's ability to bring the glucose back into the blood or get reabsorbed. So glucose levels have overwhelmed the capacity of glucose to be reabsorbed. Now, the glucose is staying in the kidney. And that has this effect called an oncotic effect. I'm getting a little more technical than I intended, but I'll really make an effort to kind of bring it back to basics. So where there is too much glucose, as it's getting stuck in the kidneys, it's pulling more and more water with it. Now that water is coming from the blood, which will cause a hemodynamic or a blood problem, which I'll mention in just a second. But the consequence of this that is so obvious is that the person is urinating a lot. So high glucose results in too much glucose getting filtered at the kidney, and the kidney can't bring it back all into the blood like it should. So the excess glucose that's staying in the kidney is pulling in excess water, which is resulting in much more urine production than normal. Now, back to the hemodynamic or the cardiovascular effect that I alluded to a moment ago. If you are pulling in a lot of water and dumping it in the urine, the origin of that water is the blood. About half of what is our blood is water. That's this plasma part. It's mostly water, enormously mostly water. And that water is what's getting lost. And so the volume of blood starts to go down. And where you have less blood volume, you have less blood pressure. And now the person has hypotension potentially. So anytime they're getting up, you know what I'm talking about. They start to feel like they're going to black out, or they do black out. Now, that's a consequence of the long-term or chronic hyperglycemia, and it's the most famous effect of glucose. And indeed, many conventionally trained individuals would stop there and say that's the end of the story. Well, it's not. Let's go further than that now. So the first point I want to make is that hyperglycemia, the more glucose is elevated, the more insulin is elevated, because glucose is the primary stimulus for inducing a secretion of insulin. Because one of insulin's most famous jobs, but I do not say that it is its most important job, is to open doors of the cells, these glucose transporters, to allow the glucose to come from the blood and go into the cells to be stored or burned. So the more glucose comes up, the more insulin comes up. The result of this then is that with more insulin comes more insulin resistance. I've talked about that previously, so I'm not going to revisit that particular effect of too much insulin causing insulin resistance. That has been an explicit topic of previous metabolic classroom lectures. But what I want to focus on is just the phenomenon of eating more carbs resulting in the need for more insulin. And as that, even in fasted states, so not just, it would be obvious that if you eat more carbs, which would convert into more blood glucose, you're going to get more blood insulin. But what if you have people that are eating more carbs, and then even when they're in a fasted state, their insulin is still much higher than what it used to be? That is insulin resistance. Remember, those two things go hand in hand. Where you have more insulin resistance, you have more insulin. You cannot tease the two apart. Okay, so I want to cite a couple studies, and you can find links to this in the show notes. So in one particular study, they fed subjects in two different diets. They were eucaloric, so the same number of calories. One was high carb, and then one was low carb, high fat. At the end of this period of higher carb or higher fat, there was about a 50% increase in the fasting insulin of the group that was eating the higher carb diet. This was just short term. This was just over 1 week. So a substantial 50%. Now, lest you think that is impressive, there was another study linked in the show notes that did something pretty similar. It was just 6 days, and they had them overeat this high carb, lower fat diet. And they found that in this case, insulin went up by double. This was fasted insulin, just in 1 week, having a diet that was much more focused on carbs and cutting down fat. In just 6 days, they're fasting insulin. I don't mean just after they ate their meal. I mean, they ate a dinner and they don't eat anything for 12 to 16 hours. Then they measure. Their fasting insulin was twice as high as in the before they ever started this. Also, just as an interesting note, their triglycerides went up significantly. And that is relevant because triglycerides are one of the more predictive markers of heart disease, far better than LDL cholesterol, despite our obsession, not mine, but our as in the sort of collective biomedical realm, an obsession with LDL cholesterol, all because of its apparent ability to predict heart disease. Well, it's a terrible predictor. Triglycerides are much better. And again, interestingly, on the focusing on just consuming more carbs, triglycerides spiked. Okay, so that is one consequence, that hyperglycemia is contributing to insulin resistance, which in turn amplifies the hyperglycemia, which in turn amplifies the insulin resistance. And you can see quickly how that becomes a vicious cycle. Okay, the next point I want to make is oxidative stress. And this is a major consequence of hyperglycemia. So here's the issue. When blood sugar is high, blood sugar synonymous with blood glucose, it will lead to an overproduction of reactive oxygen species, or ROS. I may sometimes just refer to it as ROS, ROS. These are free radicals that you've heard of. You've heard of free radicals. You've heard of oxidative stress. That just means you have cells that are making more reactive oxygen species. These are problematic because they're highly reactive, and they can damage everything from proteins in and out of a cell, DNA in the nucleus of a cell. They can damage lipids that are in cells or circulating, like in LDL. So whenever you have more oxidative stress, you have the potential for a lot of damage. Now, even acutely, hyperglycemia leads to an overproduction of reactive oxygen species because it overloads the cell with energy. So at the end of all metabolism, of nutrient metabolism, we're breaking down fats, breaking down ketones, breaking down lactate, breaking down glucose. If it uses the mitochondria, which all of those can do, all of them do absolutely. Glucose can either use the mitochondria or not. But the moment the mitochondria is involved, there's something called the electron transport system. Some people call it the electron transport chain. I call it a system. I think that's a more accurate term for reasons I won't get into. But essentially, when a cell becomes inundated with glucose, it has to metabolize that glucose in one way or another. And there's evidence to suggest, I have a paper linked here, that it actually overwhelms the first complex, the first kind of enzymatic group or process within this electron transport system that is the main area of actually producing the ATP, or the molecule that the cell needs to get any kind of work done. It overwhelms complex 1. So complex 1 is just getting these molecules overfed. It's getting stuffed, shoved in its mouth, and some of it's just sort of spilling out. And this is actually a phenomenon that we would refer to as electron leakage. So the electron transport system is so overloaded that it's not handling the electrons very well, which is giving rise to the birth of these reactive oxygen species. So that's a direct effect of hyperglycemia. In fact, a study that I've linked here had 20 participants, and in just a 2-hour period, increased their glucose levels to 15 millimolar, which is a pretty reasonable amount. That's high, but absolutely not impossible to get to. And they found that over this time, they measured a plasma marker of oxidative stress called nitrotyrosine, and it skyrocketed. So this direct marker of oxidative stress just went through the roof, just with one single bout of hyperglycemia. Now, that has consequences, including on the blood vessel, where you have more oxidative stress, you're risking damaging the blood vessel directly, and I'm going to get to that in a moment, and also altering lipoproteins. I have started talking about it more, but also my friend and colleague, Dr. Paul Reynolds, also a professor in the cell biology department here at BYU. He and I have published multiple papers together on these topics, and it has been his area of research for some time, which is advanced glycation end products, AGEs, advanced glycation end products. Now, advanced glycation end products are problematic in their own right, but the next topic we get to will highlight a consequence of that with their receptors. But advanced glycation end products are these toxic molecules that are formed when glucose or other simple sugars, fructose, in fact, fructose can do it even more than glucose can, but not all simple sugars, because, for example, allulose has little to no effect on glycation. So with glucose, because that is the topic, the glucose molecule will irreversibly bind other molecules like proteins, or amino acids, or fats, or even DNA. And all of this, as you have undergone this glycation, in fact, even the proteins in skin, collagen, and as the glucose molecule is irreversibly binding, you're damaging these things. And this is why glycation is known to contribute to things like retinopathy, or problems of vision, kidney disease, atherosclerosis, Alzheimer's disease, premature wrinkles and aging, as the glycation is affecting the collagen in the skin. So all of these tissues are susceptible to glycation, and once glycated, because of these advanced glycation or becoming advanced glycation end products, they are irreversibly damaged and then have to be cleaned off, or resolved by basically breaking it all down. So advanced glycation end products and the direct contribution that they have to chronic diseases. And I have a good paper linked that is a review on this, but it is a steady buildup of these glycation products that will affect nearly every organ of the body. In fact, I say nearly because I'm not familiar with evidence of every organ, but I suspect it is, in fact, every organ. The only measurement we have to get an idea of glycation is HbA1c. So glycated hemoglobin is the marker. That is when the glycation has occurred at the hemoglobin, not only compromising or most directly compromising the red blood cell's ability to carry oxygen, its most famous job, but it also then becomes the only marker that reflects overall glycation. Now, I had mentioned when I first brought up age formation that there's an inflammatory component to this. And this is where Dr. Reynolds, my friend and colleague, first started collaborating, because when I was a young professor, one of my primary focuses was something called a pattern recognition receptor. Particularly a receptor on a cell. So a receptor is something like a baseball mitt that is used to catching things. And the receptor that I studied was one called TLR4. TLR4 has substantial similarities with another pattern recognition receptor called RAGE, RAGE, which is the receptor for advanced glycation end products. So as much as I just got done describing the formation and consequence of advanced glycation end products or AGEs and them binding to molecules and irreversibly damaging them, we add to that this phenomenon wherein age is binding to RAGE. And when RAGE is activated, it ramps up inflammation. So anytime you can increase age formation, you are promoting this pro-inflammatory environment or milieu within the body at large. Indeed, if you look at markers of inflammation like C-reactive protein, which more and more people get measured, or TNF-alpha, many of the interleukins or the interferon, like interferon gamma, all of these are, and there are dozens of these that we could list. I could probably get through about a dozen, and then I'd have to look up the names of the rest. But there are many of these molecules that are both a consequence of inflammation being turned on and a cause, because as they start spreading through the body, they activate other immune cells like macrophages. But suffice it to say, the more we have inflammation, the more we're damaging tissues. Inflammation is something that is intended to be turned on and then turned off. It has a very specific target, like a wound. I need to heal this wound, or I need to fight this particular bacteria. When you have this metabolically derived inflammation, there's no end. As much as the person is continuing to exist in a hyperglycemic state, even temporarily, spiking it up and down, at that peak, you have the formation of advanced glycation end products. Those advanced glycation end products can bind RAGE, promoting inflammation. And of course, one consequence of inflammation is going to be insulin resistance. And then because inflammation is one of the cardinal causes of insulin resistance, but you also have just the potential of inflammation to put the immune cells in a state of aggravation, if you will, including macrophages, which can be residing in the walls of the blood vessel or the endothelium. And the foam cell represents kind of a fundamental core of the atherosclerotic plaque. So if you look at a plaque that is growing within the wall of the blood vessel, it's really the foam cells that are the main body of this. It's these big fatty macrophages. Now, when I say fat, you're immediately thinking, oh, okay, I need to eat less fat, but it's not that simple. What can happen is that the foam cell starts engulfing LDL lipoproteins. So it's engulfing the fatty lipoprotein. And that then is giving rise to this cell that when you look at it under a microscope, looks like it has little bubbles, or it looks like it's foamy, but those are actually fatty bubbles. They're not air bubbles. You never have air bubbles in the body. But that is a nice opportunity to, once again, transition into the next topic, which is hyperglycemia and its impact on LDL modification. Now, it's very important to appreciate the fact that in its native or unaltered state, LDL is totally benign. This was done well by, I think it was a group, Brown and Goldstein at UT Southwestern. They won the Nobel Prize, but it wasn't for this. But they have work showing that if you take macrophages and incubate them next to native or unmodified lipoproteins, LDL, they do nothing. They just exist in perfect harmony. If, however, that LDL has somehow been altered through peroxidation, like with polyunsaturated fats, which could do that very well, or through glycation, which is what we're getting to now. If you've altered the LDL, now it's considered problematic, and the macrophage will engulf it. It will eat it up. And the more it's eating up these modified LDLs, the more you're creating a foam cell, which becomes a very big, fatty, pro-inflammatory cell living in the wall of the blood vessel. And again, it's easier for the macrophage to get in there if you have had your glycocalyx eroded. You've lost that protective barrier. So under normal conditions, LDL is a perfectly benign transporter of fats and proteins. It's just moving them around the body, both fats for energy and cholesterol for structure, which is very important. Speaking of the electron transport system that I described earlier, one of the most fundamental pieces of that electron transport system is a molecule called ubiquinone. Wouldn't you know it, ubiquinone actually has its origins as cholesterol. It uses the core structure of cholesterol to turn into ubiquinone, one of the most important, indeed an absolutely irreplaceable, unavoidable component of the electron transport system. And indeed, it's a component that we have less of when a person is on a drug that is demolishing their body's ability to make cholesterol. So under normal conditions, LDL is just happily carrying fats. It's basically a little school bus dropping off chubby little kids, fatty little kids throughout the body, all with a distinct purpose. Now, the LDL can undergo glycation, and that can happen at this ApoB, one of the ApoB proteins on the lipoprotein. Remember, LDL is a lipoprotein. It has fats, triglycerides, it has cholesterol, and it has proteins on it. It is, after all, called a lipoprotein. Glycation is when you have now glucose, back to the advanced glycation end products, binding to these proteins. Now, it can also bind the lipids, but now it makes it more prone. It's been altered, so it directly is compromised in its structure and function, making it not a great fit for its receptors where the liver would naturally be pulling it in and clearing it out. So it's making the LDL linger much, much longer in the blood vessel, the lipoproteins, but also it makes it more susceptible to peroxidation. And so you can see with hyperglycemia, you have a greater risk of oxidized LDL. Oxidation generally will refer to us burning the fat for energy. So even though I just mentioned that it increases oxidized LDL, that really is more a reflection of the oxidative stress damage, which technically would more accurately be referred to as peroxidation, not oxidation, but peroxidation. But those terms are used pretty interchangeably. I will try to just refer to it as peroxidation, but even still, the actual tests that measure it are called oxidized LDL. That's what they say they're measuring. But anyway, just to say that all another way, with these terms in mind, hyperglycemia and will result in glycation of the LDL, which increases its risk of peroxidation. And you can get that, you can directly measure the increased LDL peroxidation. That now is a very reactive, problematic LDL. And once again, back to the work of Brown and Goldstein, that makes a macrophage much more readily to identify that modified LDL as problematic and then want to eat it up. Because one of the jobs of the macrophage is to, phage means eat. It wants to engulf these problematic molecules and sort of protect the rest of the body. So the takeaway from this sort of final segment actually is that hyperglycemia isn't just a consequence or isn't just relevant to the blood glucose and the insulin, that there's a direct modification of molecules like LDL, not to mention the glycocalyx, and not to mention the inflammation, which is putting the immune cells in a heightened state of alert anyway, but it's all contributing to this kind of perfect cardiometabolic storm. And the paper that I have linked for this segment refers to this process of glycooxidation, or perhaps to be a little more precise, it could have been glycoperoxidation, but that doesn't sound quite as good. And I'm all about things sounding good. And again, that's not my term. That's in that paper that I've linked. So to finally wrap things up, hyperglycemia isn't just, oh, my glucose levels are high. There are meaningful consequences to spiking blood sugar. Now, I don't mean to say that we can never spike blood sugar, but I do think it's important to not minimize this, that where we have the ability to mitigate that, of course, avoiding carbs avoids the glucose spikes, full stop. As much as people like to post pictures of their CGM results when they're exercising, yeah, that's a pretty slow and steady climb. And by the way, if you're in the sauna and you see a big spike, that's an artifact of the CGM overheating. It's not an actual artifact of your hyperglycemia. That's not happening. Maybe very, very modestly, but nothing like what you see on the CGM. That is, again, just a consequence of the heat affecting the measurements. But there are consequences. And so to hyperglycemia, so when we do enjoy something that's going to spike our glucose, I do think it is incumbent on us, it may be prudent, to embrace any strategies we can in order to mitigate that. Like if you're eating glucose, then there's value in focusing on fiber with that glucose. The more a person is eating carbs that spike glucose, I would say the more important fiber becomes. The less a person is eating carbs that spike glucose, the less important fiber becomes. There are other things like allulose. Of course, we have published a paper in animals on that effect. We're about to publish a study on humans documenting the same. Allulose has a tremendous ability to blunt hyperglycemia. Also, yerba mate has been shown, the chlorogenic acid, which is a key molecule in yerba mate, that has also been shown to mitigate hyperglycemic excursions in response to glucose consumption. And of course, apple cider vinegar, water extracted cinnamon, the best one of which is, I actually get one from Costco there. So water extracted cinnamon is also a strategy. And then one of the most effective of all is just going on a walk. If you can go on a walk after you've eaten that glucose spiking food or carbs or drinking them, then that really blunts that curve as well. So a handful of interventions, some very convenient, some a little less convenient, but all generally effective at mitigating the glucose spikes, which do in fact have, I would say, meaningful consequences, including inflammation and oxidative stress, damage to the endothelium, modifying the LDL, that I think we ought to keep in mind, and perhaps use that as some motivation to stay the course when we're thinking about diet and indulgences.